P-charts are a type of control chart for attributes that look at the fraction nonconforming in each subgroup. Let's take a look at how to construct these P-charts if we're given a data set with a fixed subgroup size. So our subgroup size doesn't change, it's the same for every single sample we take. P-charts are put together using the same method as for variable control charts. The first thing you want to do is select your quality characteristics. Now you can have one or more quality characteristics posted to a P-chart. So you can pick, for example, the number of bruises on the apple and discoloration, or just look at the number of bruises. Next thing you want to do is determine your subgroup size. Your subgroup size depends on P, which is the fraction nonconforming in your population. So the smaller your P is, the fewer number of nonconformities you have in your general population, the bigger your sample needs to be, or your subgroup needs to be, so you can properly estimate how many nonconformities are in your entire population. Usually you need at least 50 points for a proper subgroup. After you've determined your subgroup, you collect your data. You need at least 25 subgroups for a good P-chart. This will give you a good series of data that lets you truly see trends and not just something that may appear to be a trend because you don't have enough data to confirm. When you have your data, then you calculate your central line and your control limits, so those are your warning and action limits, and then you construct your chart using all of those that you found before. Now I said using a subgroup size of 50 was generally good practice. This is true, but if you want to be very precise in determining your subgroup size, then you would use this formula right here. So you can see by this box what all of these variables means. N is the number of in your subgroup. P is your estimate of your population nonconforming. This is not necessarily the same thing as your sample nonconforming. It's just an estimate on, in general, how many nonconformities per how much product do you expect. Z alpha over 2 is from the normal distribution. And if this looks familiar from statistics, yes, it's that same Z in your normal distribution. This is the coefficient for the area between two tails, and it depends on your confidence interval. So if you remember from statistics confidence interval, we are not really going to cover that much in this course, but just know for a confidence interval of 90%, Z alpha over 2 equals about 1.645, and for a confidence interval of 95%, Z alpha over 2 equals 1.96. So those are the two main numbers you need to use for this formula. Capital E right here is the maximum allowed error in your estimate of P. So how far you are off of the true value. This is also known as precision. So if you see precision show up in a problem, it's referring to this E right here. Whether or not you use that formula to determine your subgroup size, the next thing you want to do is calculate your central line. And that's your P bar. Bar over the P meaning an average. And so this is the sum of your NP divided by the sum of your N, where N is your subgroup size. Keep in mind that NP is not the count of nonconformities. This is not that type of attribute chart. That's a different type of attribute chart. NP is the fraction nonconforming in each subgroup. So for example, if your subgroup size is 100 and you have 3 nonconformities in that sample, your NP for that particular sample would be 100 times 0.03 or 3. But wait a minute, I just said that we're looking at the fraction nonconforming instead of the count of nonconforming. And this is true. Even though in the numerator here, you do end up, after you multiply N and P together for each subgroup, you have a number of nonconforming. You're dividing it by the total number of samples you have in all of your subgroups. So this will actually give you a fraction nonconforming. If you end up with something greater than 1 for P bar, check your math because something went wrong in that calculation. Your upper and lower warning and action limits seen here are calculated using your average P, and then this value in the square root here, which is actually your standard deviation. This is the formula for standard deviation for this chart. So your upper action limits are your average P times 3 times the standard deviation. Lower is minus 3 times the standard deviation, and then same thing for upper and warning limits. You're just swapping out 2 here because we're 2 standard deviations away from your mean instead of 3. When you get finished calculating your central lines and limits, you post everything to your chart, you're going to end up with something like this. Notice that our subgroup average, these are our average P's, are fairly low, and this is what you would expect for a process that has decent control. You're not going to expect a lot of nonconformities in a well-controlled process. If you're ending up with values 0.2, 0.4, your process is very variable, and it's producing a lot of non-conforming or defective product, and that's not a good thing. So even if you are within your warning lines or your action lines, if you've got a high average percent non-conforming here, you probably want to take a look at your process and evaluate it, see where all that variation is coming from, because you're likely at that point producing out-of-spec product. Here our percent nonconforming is fairly low, and we only have 1 point here at subgroup 17 to be worried about. So once we track down the event that caused that particular high subgroup average, then we can control our process better and bring our process back into control. This in general is how you use control charts for attributes. You take your final product and you say, all right, how is my process in general doing? By evaluating your process in this manner, you don't get a very close-in look like you do with control charts for variables where you're looking at a single process variable, but you can get an overall idea of how your process is performing and what your overall variability and percent nonconforming is looking like.